The purpose of this video is to discuss the general process and goals of database design, to talk about user views and explain their function, to talk about the database design language or DBDL and how to use it, how to create different types of ER diagrams so that we can visually represent our database, the methods that we use to create a database, the differences between physical level and information level design, to talk about top-down versus bottom-up approaches to database design, how to use existing documentation that a client would have to be able to create a database, and also how to use a survey form. Database design is a two-step process. We have the information level design, which is where we are trying to figure out what needs to be in the database without regards to the actual requirements of the DBMS. This would be like where we're trying to write it down on paper, what we think should be in the database. Once we have the actual information level design, then we have to go out and decide what type of database system we're going to use. Are we going to use MySQL, Microsoft SQL Server, Oracle, or something else? And then once we know what we're going to use, then we have to be worried about what the actual constraints are for that particular system. The actual process of taking what we've written down on paper, what we believe the database should look like, and actually getting that into our database system is called physical level design. We're going to start by creating what are called user views. Now be aware that a view, like we did before, which is a logical table, which is a logical representation of the database table, and a user view, those are two separate things. Unfortunately, they have similar names. A user view is going to be what does the user need in the database? What kind of access does the user need? What do they need to see? What do they need to be able to do with the database? That's a user view. Our database is typically going to be made up of a cumulative design that is all of the different user views. So if we have a manager and a salesperson and a low-level employee and a receptionist or whatever else, all of those people are our users, and everybody has their own requirements as to what they need from the database. When we take all of their views, what they need to see in the database, and put that all together, that's called a cumulative design. When we do the information level design, the first thing we need to do is figure out what the user view is. So we have to see what exactly does this particular employee need. We're going to go around and talk to every employee that needs to provide input. So we're going to ask, what kind of stuff do you need in the database? And we'll start taking that information so that we can provide a collection of tables that represents the data that they need. After we get the information from all of the different people that are involved, then we go through and try to normalize the design that we have. Once we normalize it, or during the normalization process, actually, we will end up finding all of our keys. Are we going to have a primary key that's made up of employee ID numbers or some other value? And then what we do is we go back through and keep doing this, and we're going to merge these steps together until we come up with one cumulative design. Now the catch is that we have to figure out who all is involved, what exactly they need, what kind of properties they need, and then any relationships between these. And then what we're going to look for is relationships between tables. Do we have a one-to-one relationship, one-to-many, or a many-to-many relationship? All right, so a one-to-one relationship is going to be where the primary key of one table points to one record in another table, and there's only a one-to-one relationship between the two of those. That is going to be our simplest implementation. That's what we really want to try to get to if possible. More than likely, though, we'll end up with a one-to-many relationship, which is where one record in one table is related to many records in another table. We had an example before of a sales rep, and if a sales rep has an ID of 35, it's possible for that one sales rep to be attached to many customers. What we do not want is what's called a many-to-many relationship. We want to try to stay away from any of the relationships where many of the records in one table could be related to many of the records in another table. We'll get more into that in just a few minutes. We want to go through, normalize all the tables. Our target is third normal form. Now, fourth normal form is our most perfect environment and everything's excellent in the way that it needs to be, but it's not always realistic. The problem with fourth normal form is we usually end up with so many different lookups that we cause the system to be slow. So we're going to try to get our system into third normal form. This does require us to have quite a bit of planning ahead of time so that way we don't we don't end up with things that shouldn't be there. We don't end up messing up other types of relationships. All right, so the first thing we need to do to normalize it is figure out what our keys are. So what are our keys in all of the tables? And we always need to have a primary key, but we need to consider other columns that could possibly be the key. All right, so when I look at a database table, let's say I have a database table where it's a list of students, and each student has a record number. So I have record 1, 2, 3, 4. Okay, that could be the primary key. Or each student has a student number, and the student number could be the primary key because each of those is going to be unique. Each student has a driver's license number. Well, that could be the primary key because each one of those is unique. Each student has a driver's license number, so those are all unique, so we could use that, or we could use a combination of all of those. So if we have a column that may possibly be able to be the key, that's called a candidate key, we're going to have to pick one of them. All right, so do I want to pick the auto number 1, 2, 3, 4? Well, I showed you earlier in the semester that that could easily be broken if you delete a record and re-add it. It would automatically get re-added as a new number, not as the prior number. So our auto increment column may not necessarily be the best choice. If you have a student ID number, every student has a unique ID number, and that may be the best choice. However, if you are a student now and then you graduate and then you come back and apply again, you may get a new student ID number. So that one could be our primary key, but maybe not. And then we have your Social Security number. Well, your Social Security number is unique. However, if I go back 100 years, somebody else had your Social Security number. All right, so that one may not necessarily be unique, especially since some people are getting older. All right, your driver's license number, same thing. That could be recycled. Okay, so if any of those could be our primary key, they're all candidate keys. I have to pick one of them, or a combination of them. All right, so what I'm going to do is something more along the lines of take your student ID number and your Social Security number and make the two of those into what's called a composite key. So those two together would make up a key, and I know that I have a very high chance of that being a unique combination of those two values. It is very unlikely for somebody to have the same student ID number and the same Social Security number repeated 100 years from now. It's very unlikely, so therefore I feel confident knowing that those two columns can make up our primary key. All right, so now that I've picked those two, the other columns that could have been the primary key, the ones that are candidates, they now become what are called alternate keys. It just simply means that those are the ones that we didn't choose, but they could have been chosen for our primary key. All right, so we have foreign keys. Now, a foreign key is going to be used to form a relationship between one table and another. A foreign key is typically used to point to some other column in another table. You need to have some sort of entity integrity here. We have to have the ability to know that if I have a foreign key, that whatever it's pointing to in the other table actually exists. So if I try to create a new record with a customer and I try to say that the representative number is 68, if I go over to the rep table, there'd better be a rep 68 in that other table. If not, I just completely broke the referential integrity of my table. All right, so we have things that are called natural keys and artificial keys and surrogate keys or synthetic keys and so forth. The question is, what are they? All right, a natural key is going to be something that already exists. So something like if you come into the school and you have a driver's license, then that driver's license number already exists. We could use that as the primary key. You already have a Social Security number, so we could use that as a primary key. Those are natural keys. Those are things that already exist, so therefore we could just already use them. Then we have artificial keys, which would be something like your student ID number. We went ahead and just made up a student ID number for you. You get the next number in line. So that one's there just for the purpose of being able to have a primary key. And then we also have a surrogate key or synthetic key, and this is going to be something like our auto number ID field. So our 1, 2, 3, 4, and so forth. Typically, we're going to try to use either a natural key if it exists or an artificial key. We want to try to avoid using a surrogate or synthetic key because the auto number system is very easy to break. All right, so we're going to start designing our database tables, and we need to have some sort of way to list what's in our table without having to draw these ER diagrams all the time. The ER diagrams are nice, they're just kind of hard to make, they're clumsy, we have to go through all these extra steps, and we can type things a lot faster. All right, so early in the semester we talked about our standard notation, which is where we type the name of the table, and inside of parentheses we list all of the columns and we underline the primary key. The problem with that is if I try to use something like Notepad, I can't underline things. And so we need some other way to list what things are. So we're going to use a pure text system called DBDL, Database Design Language. And what we're going to do is still list everything just like we did in standard notation. We list the name of the table, and then in parentheses we put all of the attributes. But instead of underlining the primary key, we're going to list it underneath as 2 letters. We'll call it a PK. And then we're going to list things like our alternate keys, if we have any secondary keys, foreign keys, and so forth. And then we can list where these point to also. All right, so in this example here, we have a table called employee, that each employee has an employee number. Now the catch here is that I can't do this in Notepad. So what we're going to do is in DBDL, we're going to get rid of this underline, and we're going to move it down here. So where this says AK, we're going to add another line that says PK, and then just simply list employee num. Then all of the other attributes are listed here. Our alternate keys, this is one that could have been the primary key. We just simply chose not to use it. That gets listed as an alternate key. If we have any secondary keys, those are also going to get listed. And then we have our foreign keys. So the foreign key here of department number points to the department table. So what this is telling the system is that, hey, this department num that's here, it's a foreign key, and if I want to know what department number 3 is, then I have to go look at the department table to find out what it is. Now, when we list it this way, we're assuming that the department table has a department num column and that it's a primary key. But in reality, that's not always the case, because the department table may have a column called ID. So if the primary key in the other table is not the same as this, we're going to actually list it in its fully qualified name. So what we're going to do is something more like department num points to department dot department num. And then that way we fully qualify it. Once we have all of our tables designed, we're going to start merging these together. And what's going to happen is you may find that some of the tables overlap each other. So it's possible that somebody in our sales department needs to have a list of all of our customers, and somebody that works in reception also needs to have a list of all of the customers. And if those two things overlap, then chances are we just simply need to make a table to keep track of that information and give both the departments access to that particular data. But then our salespeople also need to know about orders. Okay, so then we start making like a sales orders table, and then we start giving other information just to the sales department. We don't want to create the same data for 2 separate tables and then have to update it, because what would happen is, let's say we have a customer and their telephone number changes, we have to know to change it in the marketing department and in the sales department. All right, so we're going to start with information level design. That's where we write it out on a piece of paper. We always try to take all of the user views, put them all together, worry about all of our constraints, what kind of data is going to be in the fields. You know, do I have numbers? Do I have strings? Do I have characters, and so forth? And then once I have all of that, then we need to start getting into the physical level design. Now, physical level design, like I said, is going to take into account what kind of constraints, what kind of requirements, what kind of capabilities each DBMS has. Then on top of that, we're going to use the DBMS to enforce restrictions. We're going to set up security and other things like that that we can't actually list in our DBDL or ERDs. We're going to use 2 different types of design methods. One of them is called bottom-up design, and one of them is top-down design. Now, bottom-up design involves going around and talking to all of the employees. What do you need in the database? What do you need? What do you need? And so forth, and trying to build a design that way. If we use the bottom-up design, we get a lot more of the user views into the tables and into the database, and it represents what the users need to see. Top-down design is a little bit different. Now, top-down design is we're going to try to look at the general overall structure of the organization and then try to reproduce that in a database. Okay, so if I look at the school itself is an entity. We want to go ahead and make a database for school. Then we have different departments, so we're going to have a departments table. Then we're going to have, within each department, we're going to have a list of all of the types of courses that we have, so we're going to have a courses table and so forth. The top-down design generally reflects the organization of how the the arrangement of the organization. And then the bottom-up design is taking all of the user views into account. Usually when you start with a bottom-up design, you end up with a better quality database because it has more of what the users need in it. If you start with a top-down design, it will generally better represent how the organization works, but it may not have all of the views that the users need. To get these requirements, the things that the people need in their views, we're going to use what's called a survey form. A survey form is just simply going to be, I actually physically go out, talk to people. What do you need in the database? What do you do on a daily basis? What is your job type? What kind of data do you use? Do you talk to customers? What kind of data do you collect from customers, and so forth? And then what we're going to do is we're going to get these for all of the different departments, and then once we have them for all the different departments, then we can start putting them together and coming up with some sort of design. One of the things that really helps with the survey form is also to collect existing documentation. So if I go out to a company and let's say they're handwriting out invoices, we can take that invoice and look at what kind of information they're already collecting, and then we can use that to try to build things into our database. All right, so in this case we have Holt Distributors. Okay, they have the name of the company, they have an address, they have a date up here, they have an invoice number, who's it being shipped to, is it being sold to, what's the customer number, and so forth. There's a lot of information that I can get out of this table. So what I'm going to start doing is I'm going to start listing what I believe these attributes would be called. All right, so what I could do is I could say this is customer. Okay, so this is customer number. PO number, this is customer PO number. Our order number. Okay, so this is company PO number. This is order date. Okay, order date, ship date, sales rep. These are all things that I can start listing out, and I need to figure out which things belong to me, which things belong to the customer, which things are just general information like the date. Okay, so what we're going to do is we're going to start listing out what all of these things are just by getting the names of what I believe that they're called. And then we're going to try to force them to all start with customer, the customer information. And we're going to have things like items. And so for each item, we'll start with item. And what this allows us to do is start breaking it down, and we can look at customer number. What is that made up of? And then, then we have our items, we have invoices, we have orders, and so forth, and we can look at all of the things that make up those particular pieces of information, and now we have a list of tables that we need. So now we know we need an invoice table, we need a customer table, we need a rep table, part table, orders, an order line table. Where do we get all that? From one invoice. That's it. All right, so what we're going to do is we're going to go through and we're going to try to form relationships between these tables. Now remember, the one-to-one relationship is going to be the simplest one that we can use, but there's no guarantee that the data is going to match between tables, so it may not always work. All right, so what we're going to do is we're going to try to make one big table that has all the information in it that's related to our customers, one big table that's related to our invoices, one big table that's related to our items, and then we normalize it from there. All right, that's kind of cumbersome to do. So if I try to normalize all of that information out, it may or may not work. Okay, so let's put some sample data in it and see if it works or not. All right, so what we can do is we can come up with different solutions for how to solve this problem. All right, so if you look at this, we have these relationships here. We have a rep table and a customer table. So now each representative has a representative number and a name and a customer number. And each customer has a name. All right, now I have a problem here. I have a relationship where this one representative is stuck only being able to handle one customer. All right, now if we do it this way, if we say rep 20, who is Valerie Kaiser, that's rep 20. That's it. We're just simply keeping track of who the rep is. But if you look at customer number 148, which is Al's Appliance and Sport, their representative is 20, which is Valerie Kaiser. This is a foreign key that points to the primary key for this table that allows us to do a lookup. And now we have a one customer over here. So for each one customer over here, they have a representative. So if I look at it from the side of the customer, each one customer has one representative. But if I look at it from the side of the representative, each one representative could have many different customers. So we have what's called a one-to-many relationship. And as long as one side of it is a 1, it's okay. I want either a one-to-one or one-to-many. I do not want a many-to-many. All right, so here's the problem. Many-to-many relationships usually end up with us having a whole bunch of extra information in a database that can cause problems when things get updated. So we always want to try to avoid having a many-to-many relationship. Many-to-many relationships also sometimes will cause us not to have a clear primary key. All right, so we have this table, which is rep customer. All right, so we have this representative 20 is pointing to this customer, which is 148. We have part rep, so this particular part was sold by rep 20. And this customer part here, this customer bought this particular part. All right, so if I were to take these three tables and try to do a query on the three of those and put them together, I'd end up with something like this. All right, so what I would end up with is a sales table that has a representative number, sold something to a particular customer, and it was this part number. Well, that is okay right here, because if you look at representative 20 sold something to customer 148, and that something was part AT94. Okay, so what is that? We have to go look it up. That's fine. These values here, if I look at all three of these, I can make all three of these the primary key. All right, because the next one is rep 20 sold something to 148. Well, they sold a DR93. So technically, if I only look at these two columns, those are okay. But if you look at this, rep 20 sold something to 282, which is AT94. Now I start ending up with problems because now I don't necessarily know which particular part was sold to which customer. I don't have a clear primary key. Many-to-many is not a good idea because we will end up with scenarios like this where when we try to join the tables back together, then we can't figure out what the primary key is. All right, so sometimes we're going to end up with what are called nulls. Now, a null is a waste of space in a database. The problem is a null is the same as not entering any information at all, but the thing you need to remember is that our computer always assigns a certain amount of memory to all of our columns and attributes. All right, so what happens is for every field that we have, we're tying up memory, even if it's a null. All right, so what we want to do is we want to try to get rid of nulls. And what we're going to do is we're going to use what's called an entity subtype. An entity subtype is just simply a table that is designed as a way to break down one big table into two separate tables to try to avoid these nulls. Now, a null is also what's considered to be an incomplete category. It means that we're allowed to have nulls in here. All right, so in this particular scenario, we have a list of students. Each student has a student ID number, they have a name, and they live in a dorm. Okay, so this person lives in dorm 3, this person lives in dorm 1, this person, oh, they don't live in a dorm. All right, so what can happen is I could end up with a whole bunch of students that don't live in dorms, and the problem is I end up with this what's called a weak entity because it doesn't have all of the values filled out. It has nulls. And the null, like I said, is a waste of space. All right, so in this small example, this isn't that big of a deal, but if I had thousands and thousands of students, I'd have thousands and thousands of null values, and then I would waste a whole bunch of space. All right, so what we're going to do is we're going to break this into two tables. One is going to be a list of the students, so just particularly the student name. Okay, so we're going to associate their student ID number with their name. And then another table that just simply keeps track of the dorm. If a student lives in a dorm, we're going to list their student number and then what dorm they live in. And if they don't live in a dorm, then we just simply don't list it. Now we don't end up with any nulls. Now we no longer have a weak entity. We have a table that doesn't have any nulls in it. All right, so the version that we're using in our database are ER diagrams. They're called IDE F1X. I don't expect you to know the name. Just be aware that there are a whole bunch of different types of ER diagrams that are available. The thing is that in the one that we're using in our book, allows us to specify if something is a complete category, incomplete category. All right, and what that means is that if I have an incomplete category, I have the possibility of a table that has nulls in it. If I have a complete category, then it may not have nulls in it. All right, so the way that this is shown is we're going to have the actual entity. So here we have the student table, and the student table has the last name and first name in it. And it is possible for a student to not exist in the student dorm table because remember, only students that actually have a dorm show up here. So there's a possibility of having a lot more students up here than there are down here. All right, so we represent that by a circle with one line. And what that says is that it's possible that some of the students up here don't exist down here at the bottom. All right, so now the next thing is, we can break this down a little bit further. Like we could have a list of all of our students and then make another table that, yeah, we have our dorms, but we also have a list of students that are seniors. All right, so not all of our students are going to be seniors, so they're not all going to show up down here in this table. So what we do is we branch this off by the circle. The single line shows that the things that are down here are incomplete, which means there's a possibility that not every student is listed in either one of these tables. But we do also have what's called a complete category. All right, so if I were to break this down into a list of, if I wanted to force nulls to be allowed, I would state each student and then their dorm number, and there's a possibility of the dorm being nulls. And then here we could have student non-dorm. So either the students are listed here with nulls, or they're listed here with no dorm number. All right, so like I said, we want to try to get to third normal form. That's going to be our desired form, even though fourth normal form is considered to be more perfect. The thing that we're going to end up with is sometimes when you normalize the table, you end up breaking these user views. And what happens is sometimes the stuff that we believe that should be in the database, when we start looking at the views, we'll find that we've actually normalized stuff out of the database and it no longer meets these particular views. Just be real careful that when you're done normalizing, go back and look at the views and make sure they all still work. All right, so we're going to look at what's called the entity relationship model. Notice this model, not diagram. These are also called Chen diagrams, C-H-E-N. We're going to start playing with these, and these are a way for us to visually look at our database and try to figure out what's in it. All right, so we're going to draw all of our entities inside of a rectangle. At the beginning of the semester, I told you that there was a difference between right angles for the rectangles and then the rounded corners. If you go back to these, you'll see here that our actual entity, a full entity, is squared off. Our weak entities get the rounded corners. So just be aware of that when you make these diagrams. All right, so we're going to draw the entities, the tables, as rectangles, and we're going to form some sort of relationship between them. We're going to display that as a diamond. And the way that this will work is our table gets a name. So we're going to say that this is our rep table and this is our customer table. And there's some sort of relationship between the two of them. This is typically written as a noun, verb, noun type scenario. All right, so what we're going to do is we're going to look at this. All right, for each one representative over here, they could be listed for many customers over here. So we're going to list out if we have a one-to-one relationship or one-to-many. And the way that we do this is by putting the little numbers here. So for each one representative, they could represent any number, many customers. All right, so represent. So this is what's called a has a relationship. So each rep has a customer. Each customer has a rep. And we want to look at it both ways. Because sometimes what we may look at is something may look like a one-to-many, but then when we look at it from the other direction, it may look like a many-to-many from the other side. So make sure you compare it both ways and see if you have a one-to-one relationship, one-to-many, or many-to-many from both sides. All right, so we're simply going to state here the name of the table in the rectangles, the relationship, and then, so what we're going to do here with this one is the orders something part. Each order has a part. And so what we need to do is we need to list one of these as a one-to-many thing. Okay, so we're going to have many orders, and each order could have many parts on it. We have many parts, and each part could show up on many different orders. So we have to look at this from both sides. Okay, each one part could show up on many orders. Each order could have many parts. Therefore, we have a many-to-many relationship. We really don't want to do that. All right, so if we ever end up with a many-to-many relationship, then what we want to do is we want to form a third table. And what we're going to do with this third table is take the primary key out of each table and just simply form one new table that has a composite key between the two tables that is the relationship between the two of them. All right, so each one representative could have sold a part or many parts. Each part could be sold by many representatives, so we have a many-to-many relationship. So what we're going to do is we could have each rep could have sold many parts to many different customers. And so what this allows us to do is it would allow us to break it down into smaller tables and make it where we don't have that many-to-many relationship anymore. What we can do with these, we can start listing all of the attributes. Now this is an extended ER diagram. So what we're doing is we're listing that the rep table here has all of these attributes, and just like we did before, we're going to underline the primary key. And the whole purpose of this is to allow us to visualize what the table has. Now, realistically, we're going to try to just use the rectangles and the diamonds because it makes us very easily able to see if something is a many-many relationship or not. And then if it is, then we can break it into a third table. But what we can do is we can start listing that our order line table here in the middle has different attributes of its own. And then what we can do is we can look at these and say, okay, well, this person ordered a certain number of these and the quoted price was this and so forth. Now the problem is when we start breaking this down, we end up with what's called a weak entity here, or a composite entity. Sorry. The composite entity is made up of things from both of these tables here. And then we can start expanding it even further. All right, so what I want you to be concerned about is not necessarily this big expanded view, but you should be able to look at two tables, form a relationship between two tables, and find out if we have a one-to-many or one-to-one relationship. If you don't, then we need to form a third table. So please make sure that you get in the habit of always checking the relationship between two tables, see if it's a one-to-one relationship or one-to-many relationship. We also do end up with things like weak entities. It's possible that each customer did not place an order. So there's a possibility that down here with the two rectangles that this customer 103 may not have actually placed an order, but they're a customer. So there's possibility that we may not find every customer down here. All of this stuff talking about the one-to-one, one-to-many, many-to-many relationships is called cardinality. And what this is that we're trying to show somehow if these are related. Well, we don't necessarily know if it's a requirement for them to be a one-to-one or one-to-many, because it's possible if something is a one-to-one relationship or a one-to-many relationship, it's possible to have a one-to-nothing relationship also. So what we need to do is we need to start specifying that I don't want you to be allowed to create a customer unless they have at least one order. We don't want any weak entities. All right, so if that's the case, then we're going to start using what are called optional and mandatory roles. All right, so what we're going to do is we're going to start specifying this using what's called crow's foot notation. And crow's foot notation simply shows the cardinality, the one-to-many, many-to-many, and so forth. All right, so you have over here on the side, you have each one representative. So think of this as the at a minimum, at a maximum. How many are there? And then the same thing over here, at a minimum, at a maximum. All right, so over here, I'm not going to create a customer unless they have a representative. All right, so for each one representative over here, they're going to have at least, at most, look the other direction. For each one customer over here, they're going to have at least one representative, but no more than one. Those are actually going to be like ones written on there. But if I look at it from the other side, our representatives, a representative could represent no customers. Maybe we hired a rep, but we haven't given them any customers yet. Or they could represent many customers, which is represented by this thing that looks like a claw. That's why it's called crow's foot notation. So they could represent anywhere from 0 customers to many customers. Our customers could have anywhere from 1 representative to 1 representative. So meaning they have to have exactly 1 representative. All right, so database design is a two-part process. We're going to do the information level. That's where we don't care what the system physically requires. And then we do our physical design, which is where we know which system we're using and exactly what we need to put in the database. We're going to use our user views, which is where we ask the users what they need to see in the database and then try to form the database around the information that they need. The information level design, we're going to go through, get all of the user views. We're going to try to put those as tables. Once we put those as tables, then we try to normalize them. We have to identify all of our keys. And then once we're done, we try to merge those all into one cumulative design. We're going to start listing our databases using DBDL, which is where we write it out as text, and we list our primary key, alternate key, secondary key, foreign keys, and so forth underneath of the table. We can also use ER diagrams. Be aware that there are all sorts of different ER diagrams out there. The ones that we're going to use are going to be the 2-column and then also the Chen diagram. So make sure you know those two. We are going to need to use this information so that we can take all this information and put it into the physical level design. We're going to try to design our database as bottom up, because bottom up uses all of the user views, but we can do top down if we need to, which tries to represent the organization. You get a much better design if you use the bottom up design. We're going to use the survey form and existing documents to try to figure out what stuff should be in the database. All of the existing documentation should have fields in it. We can get information about what they sell, what they do, what they receive, and so forth, and all that information can be used to get to form database tables. We're going to try to get one-to-one or one-to-many relationships. We do not want any many-to-many relationships. The primary key in all of our tables, we want to try to keep those limited to 2 columns, but it is possible to be more than 2, 3 at the most if possible. If we have nulls in our table, it's a waste of space, so we want to try to get rid of those nulls by breaking the table apart as 2 separate tables. We want to try to get to third normal form, and we're going to use our ER diagrams to try to represent the database design.